Hello and welcome to a ramble. We are looking at the last question of the department's paper 2, question 10 from November 2023. So let's have a look. In the diagram, PQRS is a cyclic quad such that PQ is equal to PR. So we have an isosceles triangle. Okay, so I'm just going to, I struggle with the highlighter in this dark mode that I'm forcing, but let me see. Let's see if we use a dark color, if it'll work. Nope. We are not even vaguely winning. Man, this is such a bummeroo. That is really very sad. Okay, so I think maybe, even this works better. A light color works better. It's very strange. Okay, so maybe you know what, let's just give up on the highlighter altogether. Let's just use the pencil. So PQ, okay. Okay, so that's a cyclic quad, and we have been told that PQ and PR are equal. Oh, didn't want to write over it. Let's try that again. Okay, so we've been told that these are equal in length. Okay, right. And then the tangents to the circle through P and R. So that tangent and that tangent meet QS produced at A. Okay, so this is one straight line, tangents meet there at A. Okay, so already tangents, we don't have mention of a center of a circle, so maybe not quite tan rad yet, but tan chord, maybe there'll be opportunities. And definitely tangents meeting at a common point, we immediately then know AP and AR are equal. Okay, RS is produced to meet tangent AP at B. Okay, right, so cool. PS is produced to meet tangent AR at C. Okay, so that situation there. PR and QS intersect at M. Wow, okay, so it is a mouthful. It is a mouthful. But we have tangents, we have a cyclic quad. I don't think we have another one. I don't think we have another cyclic quad. We don't have a center, so we can't really talk about diameters and radiuses, so all of those guys are on the bench. Okay, so let's see what we need to prove. Prove giving reasons that S3 is equal to S4. Okay, so for me, when I see S4, what immediately strikes me is R3, angles in the same segment. Then I'm trying to think like, okay, what's so special about S3? Like, how would I get to S3? What other angles can I find that have that have a relationship with S3? S3 and S6 are vertically opposite. Like, we know that these are two straight lines crossing each other, so these two are equal. Maybe that can help one day someday, but anyway. What else do we see? it's on the straight line with S2, S3, and S4. It's so S3 and S2 are external angle to this triangle. So these two added up will be equal to these two added up. So that's another random fun fact. Okay, let me just write some things down. So we know that this is equal to this. Okay, and this is an isosceles triangle, so we know that this will be equal to that. Okay, and then we know that, okay, yeah, this is a bit long-winded, but you know, but I'm thinking that, okay, this is then the same as 180 minus the two dots, right? So then, and using angles in the same segment, this will also be 180 minus the two dots. And so this angle over here, S6, whoa, okay, that's giving overcompensating for these. So this would also then have to be a dot, so that these guys add up to 180. And so that guy would also be a dot because of vertically opposite angles. Like I said, hella overkill. I'm wondering if there is a simpler way, another simple way that I can find. Oh, well, oh, okay, yeah, we can completely bypass these guys, and use the fact that S6 is an exterior angle to the cyclic quad, so these two will be equal, and then vertically opposite gives us those two being equal. Okay, so let's pin all of that down. So we know that S4 is equal to R3, and that is because angles in same segment. Okay, then we know that R3 is equal to angle Q because base angles of isos triangle PQR, right? And then from there we said angle Q is the same as angle S6 because exterior angle of cyclic quad. And then lastly we said, well, S6 and S3 are equal because vertically opposite angles, and so as a result S4 is then equal to S3. Right, okay, perfect. Right, okay, cool, that was nice. I have a feeling, let me rather bring this diagram here. Okay, Right. So next the question says, prove that SMRC is a cyclic quad. Okay, so I'm just gonna draw my little circle. Oh, that is not bad at all. Like, my goodness, goosebumps. Okay, I am spending an absurd amount of time trying to get this circle perfect, and I can't stop myself. Can't do it. I don't have the willpower. Anyway, but yeah, essentially we want to prove that this is a valid circle. Right, so remember that to prove that a quad is a cyclic quad, you have one of 2.5 options, right? Either we're going to show that a pair of opposite angles is supplementary, or we're going to show that an exterior angle is equal to the opposite interior one. Those two approaches are pretty much the same thing, right? Because if this is equal to this, then that means that these two add up to 180 because these two add up to 180 because they're on a straight line. You know what I mean? So that is the 1.5 ways. The other way is to show that angles in the same segment, inverted commas, in the new circle are equal. And that's typically useful. That's typically a good route to go if the diagonals have been drawn in for you. So in this case, we only have one of the diagonals and not the other one. Of course, there's nothing stopping you from constructing, but I would say, maybe try the 1.5 ways, and if that doesn't seem to be going anyway, then maybe you can construct the diagonal and see if you can show that two angles in the same segment are in fact equal. Okay, so right, so we either want to show that this angle is equal to that one, or this angle is equal to S1, or this angle, wait, what? Oh yeah, this angle is equal to this one, or this angle is equal to that one. Hey, what looks the cleanest? I don't know. So I'm looking at this angle and I'm thinking, okay, I'm trying to see like relationships with other angles. I'm seeing tan chord, so this angle would be equal to this angle, which we don't really know anything about at this point, but hey, fun fact. Wait, but speaking of tan chord, this angle is coming from this chord, so this is equal to this. It's equal to R1 and R2, so this is also dot. And so if I can show that S1 is also a dot, okay, let me just highlight this supposed cyclic quad for myself because I'm getting dizzy. Okay, oh, that's a bad line. No, that's even worse. What is going on, y'all? Why are the lines taking off? Okay, I'm just not going to do the low trick because frustration. Okay, so this is the cyclic quad we want to, anyway, so I've just said here that this is dot because tangent, chord, angle in alternate segment. Okay, right, so then if I can show that S1 is also dot, then then my work is done, because that's the opposite exterior angle of this guy. But it is equal to dot because we've shown that S4 is dot and S1 and S4 are vertically opposite. So yeah, as nice and clean as that. So so we'll say angle CRM is equal to angle Q because of the tangent tan chord, where the tangent is AR, okay, so this guy, and the chord is RP, which is this guy, right? And then we get that angle over there from that chord. And we also know that, okay, S1 is equal to S4 because vertically opposite angles, right? So okay, we know from previously that S4 is equal to Q, previously shown. Okay, so as a result, that means that CRM, I want to play this. Okay, so therefore S1 is equal to Q, okay, which is equal to CRM, and therefore CRMS is a cyclic quad, and the reason for that is the exterior angle, which is S1, is equal to the opposite interior angle, which is CRM. Ooh, right, nice and juicy and yummy, yummy, yummy. I've got bugs in my tummy. Right, okay, so wait, let's get rid of this blank one. And let's take you to the future. Okay, right, last question asks us to prove that RP is a tangent to the circle passing through PS and A at P. So RP is a okay, so yeah, we need to get rid of this guy because that is just too much. Okay, honestly, I'm just going to get rid of this one and bring the old one. Okay, so we want to show that, well, okay, so we're being told that there's a circle that passes through PSA and P. Okay. Haha. Oh, oops, that's way too high. I got excited very prematurely there. Oh. Okay, let's try and make it a bit smaller. Yeah, that's not bad. Anyway, okay, so we're being told there's a circle there passing through PSA and P, PS and A, and we need to show that RP is a tangent to that circle. So we can do that by using the converse of tan chord, right? So if we can show that, so in this case, the alleged tangent is RP, and the only chord connecting to it in this circle is SP. So if we can show that angle P2 is the same as angle A2, then we've shown that RP is a tangent. Okay, so we need to figure out relationships until we find relationships connecting P2 and A2. So maybe let me just call this, let me call it star. Okay, and see like who is related to it. So I see, so I mean, I'm always curious about like which chord does this angle come from, and it comes from this chord, and this chord also subtends this angle, right? So this angle is also star, and this chord is also connected to this tangent to this circle. So this angle over here using tan chord is also star. Okay. What else? Speak to me, diagram. Speak to me. I'm suspicious about how we haven't used the fact that these are equal yet, I won't lie. Okay, so we do know from the previous proof that this is dot, right? And so this angle here will also be dot because these sides are equal, right? Tangents that meet at a common point. So then we have an isosceles triangle, meaning that, you know, this angle and this angle, this little bit and this little bit are equal. But if we already know that this is star, then that means that this is also star. Right. And we are trying to get to A2. Let's see. Let's keep digging. So then, because so that's also star. Because both of these are equal, so they must be the same. They must both be 2 star in value. Right. Hey, there is another way we can prove this, yes? Another way we can prove this is, so we have another chord. Oh no, sorry. The tangent is here. Sorry. I lost track there. Right. So we would like to show that this is a star as well. Well, but we know that S1 is a circle from our previous proof, which is 2 stars. And if we know that this is star, then this must be star because exterior angle of a triangle. So I mean, that is one way to do it. That is quite an intense way of going about it, eh? Is there a better way? Hey, I'm gonna commit to it because I'm hungry and I want to eat supper. So, guys, yeah, most your suggestions are more than welcome. So, feel free. Too much. Okay, I guess that can go, honestly. I don't think I need this one anymore. I feel like I'm gonna forget what I just said, honestly. Okay, so let me run through it before I erase everything. So the goal is to prove, and sometimes it's not a bad idea to write this down, right? Goal, show that angle P2 is equal to angle A2. Right, so show that angle P2, which is the angle formed by this chord and the alleged tangent, is equal to angle A2, which is the angle that is subtended by that chord to the circumference of the new circle in the alternate segment. Okay, right, so that is what we want to do. So then I've pretty much assigned a variable to this. I've said, let's call this x. And then I've said x is equal, so this is another x because tangent chord, this is equal to that, right? But then I also somehow arrived at this being x. How did I do it? Yeah, and that's quite a central piece, eh? It's quite an important piece of the puzzle, honestly. Maybe I shouldn't have been so quick to erase everything. Well, not everything, but a lot of everything. Oh, okay, I think I remember. So, no, I don't remember. So we know that, so this is x, this is also equal to x because angles in the same segment. And then, how did it come back to this one, man? Yeah, this is so frustrating. This is so painful. It makes my body sore. I could literally just stop this recording and then rewatch what I've recorded so far to find my train of thought again. Oh man, I feel like kicking myself. Okay, anyway, let's not dwell in the past, Miguel. Keep it moving. Me not talking means I'm very blank, Shem. I need, okay, let me just kick my brain into thinking here and stop kicking myself about forgetting what I said. Okay, so I'm just going to move this circle, get rid of this, get the other diagram, and just start again. Okay. Close enough. Okay, so right, we want to show that this guy and this guy are equal. Okay, so look for other angles that have a relationship with P2. So P2 and Q1 have a relationship because angles in the same segment. P2 also has a relationship with R1 because tan chord. Does R1 have a relationship with someone else? Doesn't immediately look like it. Does Q1 have a relationship with someone else? Also doesn't immediately look like it. Okay. Wait, no. So this angle will be these two added together. Okay, we know that this whole angle here is equal to this whole angle over here because these two sides are equal. So then it's an isosceles triangle, meaning that this angle is equal to this angle over here. Which is the same as this angle, just for fun, because angles in the same segment. We are trying to get all the way up here. Okay, we know that S1 is equal to CRM. This is part of what we proved in the previous question. Right, and S1 is the same as the red dots. So all of these guys are bluies in essence. Okay. Oh, okay, wait. So then, since this is a bluey, and we have a triangle here, so this is an exterior angle to this triangle, and we know that this is a heart, then this must be a pinky, because pinky and heart added together give us bluey. Oh, yeah, good luck to me writing that out. So let angle P2 be equal to X. Okay, so what do we need for this to work? We need P2 to be X and P1 to be Y. Okay. So we then we know that, okay, so we need to show that this angle is equal to this angle, so that we can show that, okay, these two then also add up to bluey. And to show that this angle is equal to this angle, we will use the fact that this angle is equal to this angle, and this angle we have shown to be equal to this angle, which is equal to this angle. So we need to show this is equal to this. We will do that by showing that this is equal to this is equal to this is equal to this. Okay, so let us do that. So maybe we don't quite need this yet. I'm just going to put it away for 2 seconds. Okay, so we are going to start out by saying angle A, left a hat behind. Okay, we're going to start out by saying angle APR is equal to angle A, okay, let me write it and then I will justify it better. ARP. Okay, and the reason for that is because it's base angles of isos triangle APR, but we need to justify why that's an isos triangle. So we'll start by saying the sides AR and AP are equal because tangents from same point A. So therefore triangle APR is is isosceles. Okay, and then we can say that this and this are equal. Okay, and then we know that we've already shown that CRM, which is the same as ARP, so I'm just going to keep with the nomenclature. ARP is the same as angle S1, right? So I'm just going to add a little that this is the same as CRM, right? CRM is that one, ARP is, you know, longer arms. Anyway, so it is the same as S1. This is already proven in a previous question. Okay, and then so we have so we've connected this, which we can connect with S4. All right, and we've already shown that they're equal. S1 is equal to S4. It has also been proven, but you know, it's easy enough to also say vertically opposite angles. And so therefore, this helped us to arrive at the point of saying that angle APR is equal to angle S4. So this guy is equal to that guy. Right. And so now we can say this little bit here. Okay. So we know that this orange angle is made up of pink and blue. Okay. And so if S4 is also an orange angle and it's an exterior angle to this triangle, then it's equal to these two added together. And since we already have the blue, then this must be a pink. Okay, so let's write that algebraically. So therefore, angle APR is equal to X plus Y, right? And also importantly, S4 is also equal to that. So APR and S4 are both equal to X plus Y, right? So then we know that angle A2 plus angle P1 is equal to the exterior angle of the triangle, so it's equal to S4, because exterior angle of triangle APS, okay, and so yeah, we don't know what A2 is, but we know that P1 is Y, so A2 plus Y, and we've also shown that S4 is equal to X plus Y, right? And so therefore A2 must be equal to X as well, right? So it's also a pinky. Okay, and so what have we done? We have now shown that A2 is equal to, okay, might as well keep it pink, is equal to the original X, which is P2, and so RP is indeed a tangent to the circle, because we've shown that the angle between this chord and this tangent is equal to the angle that gets subtended by that same chord in the alternate segment. So so therefore RP is a tangent because converse of tan chord. Right. I'm just going to look at the memo quick, and I highly doubt that I have the brain power to see the alternative approaches that they will present, like to really see them. And my laptop has also died, just symbolically, so we're just gonna believe me. And of course, you know, if you saw another way of doing it, share. Yeah, I'd really love this to be a space where we can exchange ideas and approaches and wara. Right, thank you for tuning in, and catch you next time, where we'll be starting a fresh series of questions from a new exam paper. Cool beans.